So while we're transitioning here, one of the things that we were asked to do by the John F. Kennedy Library Foundation, Stephen and his colleagues, and with Jeff and the USRA folks, was to sort of highlight some of what's going on at Rice. One of the things that came out of the Apollo mission, I think technically, although someone said, I was talking earlier, was maybe the Manhattan Project, but one of the things that came out of the Apollo program was the kind of phrase Moonshot. And so we now use it for almost everything about these sort of major scientific challenges that we have that may hopefully benefit society and take resources. So I am very honored for this. This is a very distinguished panel we have here to do our future panel. I think they're going to introduce themselves, and you're going to get a break from me, thankfully. Our moderator is going to be our very own Dean of Natural Sciences, the Weiss School of Natural Sciences, Professor Peter Roski. So he's going to take the floor and lead the next discussion. Thank you.
Well, it's a great honor and a great thrill for me to be here this evening. I am a child of the space era, and I remember when I was in second grade and Sputnik was launched, and I thought that was really amazing until I discovered by watching my teacher that it was a very dark day. And I had to have my parents explain why the first satellite launch was a terrible thing. It took me a few years to understand politics. But I think I watched every NASA launch live on TV until 1986, when I happened to be giving a seminar at the time. I was already a tenured professor. So I told David, I think, when I came here 6 years ago, that if I knew I could be someone involved in the Space Institute, I probably would have settled for a lower salary. But so I'm very honored to be moderating this panel. As David said, you know, the word moonshot now means something that's an amazing target, something that's very hard, very important, and that we could imagine, because of our history, that we could achieve it. And there are many such things that people tackle now, and what we've done is assemble 4 individuals very knowledgeable about some of the most pressing and amazing things that we want to solve: cancer, quantum computing, artificial intelligence, purifying water, and I'm going to let them introduce themselves. They're all incredibly accomplished scholars, and I'm going to let them introduce themselves and tell us a little bit why what they're trying to do is a moonshot for mankind. Do you want to start, Keelan?
Sure. Good evening, everyone. My name is Qilin Li. I'm a professor in the Department of Civil and Environmental Engineering here at Rice University, and my research deals with mostly advanced technologies for water purification, desalination, and wastewater reuse.
I'm José Onushik. I'm a professor in physics and astronomy here, but also has appointments in chemistry and biosciences. And it's interesting to see that basically how you need to put lots of things together to solve big problems. So here's a theoretical physicist that came to Houston because I want to start work on cancer. So that's interesting. I may tell a little bit more about it as we come along.
So I'm Doug Nadelson. I'm the chair of the Department of Physics and Astronomy, and I also I'm what you call a condensed matter or a solid state physicist, and I'm the one who's going to tell you about how quantum computing is going to revolutionize everything if we can get it to work.
My name is Moshe Vardi. I'm a professor of computer science at Rice University, and my research area is artificial intelligence, and I try to teach computers to think.
So perhaps rather than go directly to questions, since it's not audience questions, since these are not necessarily quantities that people are familiar with, what the issues are, maybe each of you could describe what you see as your ultimate goal and what you see as the grand challenge to get there, whether it's a series of technological accomplishments like it was in the moonshot, or if there's one big obstacle that if you could get through it, it would be a breakthrough. Is that Keelan?
Yes. For my field, what I really passionate about and really dream to do someday is find a completely new way to supply water to our cities. And we've been using the same water technologies for over a century now. In the developed countries, you have very large-scale water and wastewater treatment plants where you treat the water, take the freshwater sources and treat it, and then send through miles and miles of pipeline to individual household or industrial users. That technology has been very effective and very low cost for us, and we've used it to greatly improve public health for the last century, but it is also suffering from a lot of problems. We know that moving that huge volume of water takes a lot of energy. We also know that in that system we don't have a lot of flexibility. So every system is very chemical intensive, energy intensive, and also complex to operate. In this country, our infrastructure is also aging, so you can experience problems in water quality with the formation of toxic disinfection byproducts in a very long pipeline because water spends a lot of time being transported in these long pipelines. You can also have regrowth of pathogen. Maintenance of these systems is also very expensive, to be honest, and we can't really afford that. In the meantime, in developing countries, they can really copy the same model because they cannot afford this very infrastructure-intensive method of water supply. So our vision is to develop really smart water systems, smart in the way that it can utilize whatever local energy sources and there is, being it waste heat or solar or wind or wave, and also being able to treat different sources of water. So if you're in an area that has very limited access to freshwater sources, the system can treat seawater, wastewater, gray water, brackish groundwater, and also smart in the sense that it produces water to the level of quality that they really need. Today, we treat all our water to drinking water quality. We use our drinking water to flush our toilet, to water our lawn, to wash our car. And only a small fraction of it is used for drinking. That makes no sense given how energy intensive water treatment is. And so these smart water systems will hopefully be able to tell how much demand is for potable water, how much is for non-potable water, and treat to that level of quality needed. Being able to be used in an environment that does not require massive infrastructure, miles and miles pipeline, and huge water and wastewater treatment plant. So that's what we're working towards, and I hope that in my lifetime we will be able to see that happening.
Jose, tell us how theory is going to solve cancer.
So the moonshot is a very interesting word. Comes with the idea that basically, can we solve a big problem, bring the entire society together to solve something that has a major impact in the nation or something that brings all the spirit together? Cancer has been a word like that, basically. We had the first war on cancer by Nixon that went pretty much nowhere. And that tells you a little bit about how you deal with problems on that spirit, is not only you have to have the commitment and the idea to do it, but you have to have the knowledge at that moment, and you have to have the people, you have to have the background to go after that. So these days, I think that's an important lesson for us, in a sense, to make sure that, as we talk all the time, that we have the right, more than money, that we have right the people's network, the human resource that we need to solve the problems to create that moment. Together with that people, we have to have the knowledge at the moment. You have to be the time where the knowledge, maybe we don't know everything, but we know enough that I can tell you by 2024 I'm going to do something. You have to do this commitment. Although the war on cancer on 71 is not, right now is doing much better. Although we have seen lots of disasters, it's amazing that if we compare to the 70s to now, you have several cancers where by learning what we know about molecular biology, by knowing what we know about new biochemistry, more that stuff, with this development on the immune systems and all these new technologies, you see the cancers like most 90% of the leukemias, people are cured. A lot of prostate cancer and breast cancer is solved With immunotherapy that's coming out now, the Nobel Prize just came in town, basically with Jim Allenson, we figure out that now a lot of lung cancers that had no control, particularly small cell lung cancers, people are not being cured, but they're living for another 10, 15 years, 20 years. But it's still some areas we don't know enough. We cannot do anything about liver cancer and prostate cancer and pancreatic cancers or things like that. So cancer is a broad thing. But what's happened here is why have we able to solve all these other things that have been very successful? A lot of this success being done in Tau. Because we're bringing lots of cultures together, not only knowledge of biology, but the idea of understanding complex systems. This is a complex system. That's where theory comes in. Can we model that system? There's a lot of new computational approach that we need because we're dealing with large quantities of data. So when you're dealing with this problem, that really becomes now a complete different, say, moonshot than basically we had before, is something that comes that you have to bring these different expertise together. Now, going to the discussion we have the previous panel, when you bring all this expertise together, not only you cure cancer, but people learn to do other things because now you're bringing people with different talents. And people figure out they can solve other problems they never thought about solving other problems. And I think that's one of the things I want to point out, that basically that's the reason I moved to Houston. It's just an amazing thing. It's an amazing thing that you live in a place now that I can go and talk to physicians at MD Anderson, talk to them, write papers together. When could you imagine that you could have a theoretical physicist working with people that were physicians at that time? And this is the day that we can go after this problem by bringing together theory, model of complex systems, together with a lot of experimental information, and then large quantity of data and try to make sense of it. We are the data of big data. The question cannot deal with data without thinking about it. It's just not so this is what we are. So for some systems, we can solve the problem because the data is enough for us to learn and people are getting all the way to the patient. But I think that's basically cancer is going to be a moonshot for many, many moonshots because we have many, many different cancers. But I can tell you that although we have very bad news, you see, for some other things compared to 10 years ago, we are in a great time. But it's very important for these problems to create the moonshot because that's the only way of bringing communities together. It's the only way of funding people together. People say, really, you can bring all this talent together. But more important, we have to train new people that can come and bring this success.
Doug.
So quantum information science is analogous to a moonshot right now because there is, in fact, a national quantum initiative. I don't know how many of you have heard of this, but this was passed by Congress last year. And in fact, the similarity to the space program extends to the fact that some fraction of this is motivated by fear of what foreign powers are able to do. So what's the idea here? So you've probably all heard of the expression Schrodinger's cat. This is the idea that if you're able to look at matter on a scale where it really behaves quantum mechanically, you can get very unintuitive things going on, like a cat that can, in this thought experiment, is sort of a combination of alive and dead at the same time. So if you can control matter on that scale, instead of having a bit in a computer that's a 1 or a 0, you can imagine having a bit that is somehow both a 1 and a 0. If you have 8 bits, instead of having just certain discrete combinations, you can imagine of putting these 8 bits in what's called a superposition and having all possible combinations of them at the same time. So on the computing side, the idea is that there are certain classes of problems you will be able to solve. If you can really do this, you will be able to solve certain classes of problems extremely quickly that you could never solve on classical computers. The most famous example of this is factoring. So all of our encryption that's used out there for the most part is based on the fact that it is really, really easy to multiply giant numbers together, and it is very, very hard to look at a huge number and break it into factors. If you have a general purpose quantum computer, it is already known how you would do this, how you would take factoring and make it quick. There's database search, there's ways of simulating, of understanding chemical structures. There's a whole bunch of ideas about what you could do if you had these quantum computers. And I should also say, it's not just quantum computing. There's sensing. There's ways to, if you can control matter at these scales, this is the key to the atomic clocks that are really responsible for GPS. You can also do quantum communications. Imagine and this is the thing that the Chinese did that scared a bunch of people. You ought to be able to send completely secure communications in the sense that you could distribute keys in a completely secure way and know for certain that no one was eavesdropping on you. right? You can basically send unbreakable encryption. So there's a lot of potential to be had here. It is technically extremely hard because you're trying to balance two competing things. To do what you want to do, you need to have exquisite control. You need to be able to reach into your systems and do just what you want with them. But at the same time, in order for these systems to remain in their quantum state and not sort of collapse is the term into classical behavior, they also have to be very, very isolated from the rest of the world. So you're trying, on the one hand, you want to be able to reach in and fiddle with everything, but on the other hand, you want these things to be completely isolated. So there is a big national effort at this, and it's also a very large commercial effort at this. Intel is spending a ton of money on this. Google is spending a ton of money on this. Microsoft is spending a ton of money on this. A lot of the federal research on this historically has been funded by the National Security Agency, not necessarily because they want to read your email, but they want to know if someone else is able to read your email. So it's a very exciting time. I had a colleague here who asked me, what big societal problem can quantum information address? And I said, the timing is such, that's like asking someone in 1946, what are you really going to do with digital computers? Right? It's really early days yet, but it's a very exciting time.
So Moshe Vardi, he'll talk about, I want to point out that artificial intelligence is the only one of these I've seen advertised on TV by multiple vendors. So you have a more challenging thing to do here.
So I think there are three very, very kind of huge, big questions in science. One is the nature of the universe, the structure, the dynamics of the universe, cosmology if you want. The other one is the origin of life. I mean, evolution tells us how life evolved, but it doesn't really tell us where this life comes from. And part of the question, do we have life on other planetary systems, have to do with we don't understand how did life arise in the first place. And the other one interests me is the nature of intelligence. So kind of what makes us unique is our intelligence, but we still have a very poor understanding of it. And there are various ways one can try to study intelligence. One is to take people and put probes in their heads, and this is partly what neuroscientists do, try to understand really the hardware, what we call the wetware that you have inside our brain. And other people look at it from the behavioral point of view, maybe psychologists and cognitive scientists. Computer scientists try to understand intelligence by building it. So if, again, it's the analogy, instead of trying to understand aerodynamics, how do birds fly, let's try to build a flying machine. Let's try to build intelligent machines. And this started, as I said, the term artificial intelligence was coined about 60 years ago. And it's a field that always has periods of enormous enthusiasm. We are just at the threshold of some immense breakthrough, and then huge valleys of disappointments. And right now we are in a period of enthusiasm. You may all have heard of deep learning. So deep learning is based on an idea that actually goes back to the early 40s, and it's based on our understanding of how the neural system works. And there was, if we can try to mimic that and build neural nets, and we can use them to do, for example, recognition and classification tasks. And as it goes back to 1943, and there were again periods of, we're just at the throes of breakthrough, and then huge disappointment. We call the AI Winter 1 and AI Winter 2. And over the last decade, again, there has been real breakthrough, and we are now able to do, this is what deep learning comes in, means you have several layers of neurons, essentially artificial neurons. And now we're really able to do things that were considered just very, very, very difficult before. I mean, for example, to do a translation of languages, we try to do it by linguistics, and that proved to be very, very difficult. Then we try to do it by statistics, learning a lot of patterns of words, and that was not, if you may remember, even like Google Translate, just from a few years ago, it was give you pretty bad translation. And now we are using neural nets to do that, and we get much better translation, and we can do face recognition and image recognition and machine vision, and part of all the enthusiasm about the possibility of autonomous driving is based on the fact that we think that now machine can see. At the same time, learning is a kind of a big task of intelligence, is learning. But it turns out that learning is still very, very difficult. So if you think about it, how many people here know what is a tov? Tov, Jabberwocky. It was brilliant and precisely tov. So suppose you show me a picture of a tov. You have to show me a few pictures of a tov, and I will be able to recognize tovs. You don't need to show me too many examples of tovs. I will be able to recognize tovs. But deep learning today, you need to show them, if you want to train them, you need to show them not thousands, not tens of thousands, but hundreds of thousands of images. And you can imagine the energy cost of learning, of training on hundreds of thousands of images. Well, we're able to study, I can look at 5 to 10 tovs, and I know how to recognize tovs. So big challenge of us, what is it that we are able to learn so efficiently? And now, after 60 years of working on neural nets, we have to, it's a still enormously heavy computational task. And in fact, much of the progress of the last 10 years was because we developed very specialized hardware. So you have companies like Google, and they're building specialized hardware just to implement these learning algorithms. And I can recognize TOV by looking at 5 to 10 examples.
So if you have questions you'd like to address to any of them or general questions, please make your way to the microphones. And we'll be happy to start over here.
My question is in regards to artificial intelligence. After some reading and experiencing using some systems that claim to be artificially intelligence, I coming up to the conclusion that that intelligence doesn't really reflect human understanding. Let's say an intelligence system is trying to predict my choices when I'm searching, and sometimes some results are something I didn't even know that existed, and I'm thinking, how can this intelligence system is relating this search, this concept, to things that I have no clue existed? Now it's making assumptions about my likes and my possible shopping spree. So what I'm seeing in this artificial intelligence pursuit is that it has a limit and it has strengths, but definitely not close to human intelligence and human understanding. I see that human understanding and intelligence has a creative factor. It has an instinct, gut feeling, interpretation of fact, like you mentioned. Maybe a human can learn how to identify anything with 5 images because you bring into the play your prior experiences. In your childhood, you learn something, you remember, you pull in from your experiences in your human experience, and you make decisions. And that's not happening in artificial intelligence. So my question is, your point of view of limits in artificial intelligence, and where do you see the strengths? So maybe we can focus on the strengths so we can have more useful and powerful artificial intelligence, and whatever is human, maybe leave it to the humans, if you have that perspective. Thank you.
So it turns out it's actually very difficult to define intelligence. And we have another problem when we have to talk about human intelligence, is that we have a subjective feeling, okay? So people, for example, have wondered, can machines feel pain? We can try to train a robot to recoil from heat, but does it feel pain? But it's very hard for us to define what does it feel, what does it mean to feel pain, other than what we are really feeling. So the goal in AI is not to produce human intelligence. That's what we call artificial intelligence or machine intelligence. Instead can machine perform intelligent tasks? So there are certain things that we thought require intelligence. We thought that playing a very good game of chess requires intelligence. We think people play chess, they must be very smart people if they are very good players. People who play Go, we think they must be very smart to play the game very well. Well, machines can do it better than people. So now people say, oh, playing chess doesn't really require intelligence. We have dismissed it because machine won. It reminds me, when I was 14, my 9-year-old brother started beating me in chess. And I told him, it's a child's game. So the question is, what can machine do? And not saying how human it is. Now, for example, can machines be creative? So again, take out the emotional content that you think of creativity. And you look at it, can machine write poems that people will say, oh, these are interesting poems? Can machine create paintings that people say, wow, this looks like an amazing painting? And there is an area of research called computer creativity. And again, you have to take it in not, is it creative as people, but does it have some feature of creativity? And the answer is we're making such progress in that I think it was maybe a year ago that, the Christie sold work of art by AI. And so now you can find actually articles that are asking if AI creates a piece of art, can we say that this system is an artist, or maybe the person who developed the system is the real artist? So now the philosophical debate, what does it mean to be an artist? And only happens because we have computer-generated art that people are saying, wow, this is impressive art. It's going to be somewhat different than the way human do it. There is some talk about artificial general intelligence. Okay, so we are an amazing package of many, many intelligent talents that we can do at the same time. And if you think about connect to the space mission, think what happened with Apollo 13, the degree of creative problem solving that was demonstrated, both by the astronauts and by the people on Earth, by the engineer on Earth. Amazing creativity to bring these people back. We are nowhere near being able to build machines that will demonstrate such feats of creative problem solving. So ultimately, it's an open question. Just as the open question is, which is still an open question, can we build quantum computers? It is an open question. Can we build artificial intelligence that will be able to compete on a very wide array of tasks with human intelligence? We'll have to wait another 50 years and see what will happen.
Yeah. We'll go here and then over here next. Go, please.
Okay. First, I have a little bit of a kind of a greeting for Jose. Hispanic Heritage Month begins on Sunday, September 15th, ends on October 15th, so I just want to say enjoy. But my question is, the burning question for probably just about anybody in this room that's had a family member suffering from cancer, how close are we to creating a chemotherapy or some other kind of therapy that will kill only the cancer cells, unlike what chemo does when it kills healthy cells? Kill only the cancer cells.
Okay. That's the goal of everything. The idea is I'll be a little bit more restricted than you are. We don't have to kill only the cancer cells. We'll make sure that we don't kill too many of the other cells that cause damage. You can kill a few of them. So conventional chemotherapy comes from the idea the cancers have to reproduce very, very fast, right? So the idea is the other cells are reproducing very, very slow. So you try to say if they are not reproducing very fast, they die because the nature of cancer, right? So they say if I put some drugs that kills every cell that's reproducing, that's what chemotherapy does, the ones that are doubling, they're multiplying very fast, I kill them, I stop the cancer the others do. But there's a lot of damage that goes with that. That's where immunotherapy is helping these days. What's the idea of immunotherapy? You expect that now your immune system does the job of killing the cells. The problem is the cancer cells are very similar to the regular cells. So if you send immune drugs, they have a difficult time identifying these things. So what you have to do now is to identify what are the few proteins on the surface of the cells that only exist on the cancer cell, but they don't exist on the regular cells. And now I teach my immune system to amplify that signal. So the idea of immunotherapy is an amplification of the signal that happens on that. And then on the cells that were lucky enough to have enough different proteins, people have been very successful. That's why on lung cancers, there's some small cell lung cancer now, you have things that save 2/3 of the people, but 1/3 still die. Why? That 1/3 was unlucky enough not to have that protein on the top of their cell, so you cannot do these things. So in a sense now is, how can I combine these therapies? So what you're trying to get for your answer is the following thing. The more I can combine therapies, the more I can kill cancer without causing damage. Because if I do a cell or I do a particular chemotherapy that attacks that cell, I do immunotherapy that attacks that cell, and now I have a multiplicative effect of attacking that cell, but the damage is not multiplicative because the thing is just that cell. That's what you have to do. And that's why combined therapy becomes very interesting. But more interesting these days come how do you apply multiple drugs? And that has been successful in many cases. The case of, I think the most common case not on cancer is HIV, where this cocktail of therapies pretty much doesn't cure the disease, but you have people living for a long time. People are trying to get the similar things on that. And that requires now to know how do the system react to these things. And in nonlinear systems, it's not a system where you just can add things and do an addition. You have to figure out how the system responds. So now you have all entire new theoretical modeling of seeing how your system responds. So combined therapy, understand how the system responds, and these things are going to do better. And in some cases, we have been successful. In some cases, it has been a disaster. Some cases where we have identified these proteins or these things have been doing. But that's the goal. It's combined therapy is really learning how your immune system behaves better. And more than anything else, what people are doing these days is actually personalized medicine. Basically, these days in a lot of immunotherapies, you get the patient, you take their cells out, you train them outside, and you insert back into them. And that's a beautiful area coming together. And I think that a lot of us, in our families, we had people that we lost them to cancer. But in many cancers, we're getting less and less people dying to cancer. You hear less stories of people dying from breast cancer. You hear less stories of people dying from leukemia. However, if you have someone on your family that had liver cancer or pancreatic cancer, we have a problem. And the problem here is not because we don't know the biochemistry and molecular biology, it's because the fiber protect the cancer is so big, I cannot get the drug in there. So basically, and that cancer is so protected when it comes, so these are things that we don't know anything about it. How do we attack the cells in between and not even the cancer cells to get there? And that's a big area of research these days. So not every cancer is the same. I think we are much better there, but there's much more to be learned. But sort of combined therapy, different multiple drugs, and this effect may allow you to be more focused on the cells you're against and cause less damage to the other cells that you have. Because one thing you learned, you just said, I'm going to finish here, is that it's not enough to give more drug because you may kill the patient. So the question is, how do I kill the disease without killing the patient? And that's always the threshold of most cancer therapies these days.
Hello, my name is Willie Lowe. Dr. Nadelson, I was in your class in 2012, intro mechanics. But anyway, the theme of this whole seminar, I guess, is moonshots. So like progressing technology, trying to go for things that seemingly impossible, but maybe with collective human effort, we might be able to reach it. But with increase of technology, you have increase of potential to do good, but you also have increase of potential for people to use it for bad. So as researchers, I know it's kind of hard to think of a bad use for curing cancer or clean water, but as researchers, how do you guys deal with the potentially ethical consequences of your research?
So at the moment, I think that where ethics intersects this issue of quantum information science really is not so much at the technical capability, but it's sort of at the motivation of why people want to develop some of these things. I think there's, I mean, it's a little like, to rely on the digital electronics example again, right? Digital electronics can do many, many, many things. It can do many good things. It can do many bad things. It's a tool more than anything else, right? And so, you know, I think we all, I know Moshe is very involved leads an effort here about thinking about the ethical and societal implications of technology. And so I know we all think about what's the societal impact, and what are the ethical things to do. I think, I suppose artificial intelligence is the one that not to put words in your mouth, not to put you on the spot, but it seems like artificial intelligence.
Go ahead,
is the
put
one,
me on the spot.
Artificial intelligence is the one that has the closest connection to ethical things, because we can already see ways it can be terribly misused if you wanted to.
So I'll try to be very brief. That I think that in some sense, in my opinion, the ethics lens is a bit overstated. The right way to think is not about ethical, but societal impact. And it is true that there has been some attitude of some people call it techno-utopianism or techno-solutionism. The solution to every problem is more solution to any problem by technology is more technology. And technology will lead us to some kind of a utopia. And I think attitudes have changed over the last few years, and now we understand that technology is a two-edged sword, and you always have to think about the benefits and balance the benefit against societal cost. And we have invested more in developing technology, and we have not invested enough in learning how to control technology. So we have just launched at RISE this year a new initiative on technology, culture, and society that we foresaw your question. We act on it already in January, and we announced an initiative that aimed to study the interplay between technology, culture, and society, understand how technology can have adverse societal impact, and trying to follow the use of technology and try to mitigate the adverse impact.
Thank you.
I wanted to ask about the overlap between the areas. How can quantum computing affect AI? How can AI and quantum computing help cure cancer and provide clean water for the world?
So, it is known. In some ways, there are people who are already thinking about developing interesting quantum algorithms to do deep learning more efficiently, more effectively, right?
Yeah.
So there are definitely people who are thinking about exactly the question about if you had quantum computers, would it be easier to do certain machine learning tasks, certain artificial intelligence tasks, than if you had classical computers? In the same way, there are people who are very much interested in using quantum computing and quantum algorithms to do optimization problems. This includes like drug discovery, database searches, image analysis, so for medical imaging, right? So because it's such a generalizable tool in principle, the quantum information stuff could be applied to lots of things.
So when you model any complex problem, and cancer is the prototype of a real complex model where you try to understand the entire dynamics of these systems, part of it you try to learn from data. There are lots of experiments going there. So you create these models and you're trying to learn from data. Now, when you learn from data, one thing that you're going to do on these things, what's signal, what's noise? How do you separate these things? And this becomes a very daunting task. So any development that can come from AI on recognizing patterns, something that comes modeling with a model that tells you how is the complex, the deep learning that you have. That's basically, if you have a model, it can tell you how many layers you need to put in terms of to learn these things. So these areas are intricate. Lots of problems today is we are dealing with big data in many other different fronts. So basically, that's why I said on the cancer, the idea that basically you can have a theoretical physicist working together with physicians, with a lot of engineers and other people in the middle. That's the reality of today's science. And I think big problems these days require this sort of bring the science together. So I think less and less we care about giving titles to science. We just care about big problems and what it takes to solve the big problems, bring all the talent that you need to solve them.
Artificial intelligence is already emerging as an important tool for smart water systems. I sort of mentioned a little earlier. our water and wastewater systems are massive, especially for big metropolitan areas. And there are so many places things can go wrong. And so these smart water systems we visualize will have a lot of distributed sensors that will be producing a lot of data and a lot of signals. And so using tools like machine learning that would allow us to analyze these signals and data and telling us where you might have a leakage, where you have water contamination in your drinking water distribution network, where you may have a broken pump or broken valve. Those are all very important to manage complex systems like a water system. And people are using that already to look at possibility of doing asset management, meaning we look at our huge water supply system as an asset, and how do we use artificial intelligence to teach us about this system, because right now, just manually, we can't understand the behavior of such a complex system.
Thank you.
Thank you. Next on the right.
Yeah, my name is Joel DeJean with the Schiller Institute and the Rouge Political Action Committee. And this may have come up before, but I missed the beginning. One thing that would really revolutionize desalinating water is the availability of fusion power. And fusion-powered spaceflight would also help us to get to Mars in a matter of days instead of months. Is there some thought of using quantum computing and artificial intelligence to help crack the code of how the sun does fusion and recreate artificial suns on the Earth and in near space?
So fusion, fusion is a long-standing problem, a long-standing challenge. It's very, very difficult. There's a lot of advances in computational techniques to try and understand plasma physics. And so in the very general sense, yes, I think, any advance in computational technique is probably a plus in trying to get fusion to work. I think there are many challenges in fusion, though, that are not, there are some serious engineering challenges that are more materials challenges and controls challenges than they are computational. So
let me add just one thing to it. I actually think that on the idea of the moonshot is that if you have a problem, and I think people did great, you put a target, you put a date, you try to solve it. If you find a solution, you get all the excitement before. Fusion had many excitements like that, but the problem is so difficult, people haven't been able to deliver it. The last effort that was ITER, this international effort in putting fusion, people haven't been able to reach long enough to keep the momentum of people putting enough investment as being a macro investment in that area. So I agree with you, it would be a great problem to be solved. The sun has solved it for a long time. But on Earth, we have had a very difficult time, but I think every time major effort came into it, the momentum came down, and ITER right now is sort of dwindling down. And the people that really believe in fusion are very, very unhappy about it, but it's one of these things. So the problem with the moonshot, and I think it's great on these things, is it's great to do these challenges, but you want to make sure that at the end you get somewhere so you can keep the momentum moving. And that on this one, I think we haven't got it.
It would have been very different if we failed to get to the moon.
Yeah.
Right. So I think we'll take the people who are standing, but I think the attraction of the wine is drawing people out. So, or some kind of and the book signing, yes, absolutely. So please.
Proposition, advanced technical civilization requires a livable environment. Many, many years ago, the director of the National Academies was at that podium. I asked, based on what scientists were telling us, it looked like we needed to have some form of carbon capture and storage in order to save our bacon. The answer was yes, indeed, research was being done. Papers were being published. There was no moonshot to bring that to practical reality. More recently, scientists have said we need to cut our emissions in half by 2030. What has actually happened over the last several years is that global warming has accelerated. And my general question to the panel is, do we see reasonable paths to where we can get the moonshot of speed and scale that we need to deal with the climate crisis?
It's politics, not science.
It's a question of political will. If you can't, if a supermajority large enough to really move big bucks around, whether this is a political supermajority or an industrial supermajority, if you can't mobilize the will of people with enough power to do anything, it's very, very hard to fix that problem.
Yeah. In terms of technology, there's certainly a lot of advances in technology to pull carbon out and become a carbon neutral situation, but you have to make people do it. And I mean, recently, you probably noticed that the rollback of the methane rules, that ExxonMobil and other oil companies came out and said, no, this would basically, right, exactly, it would kill the oil companies if you did that. So we're making progress, I think. Please.
I have two questions. One is technical, one's a little bit more philosophical. Anyway, the first question is about the question of quantum entanglement. And is it possible that this breaks the speed of light? Is it possible, for example, that communications with Mars, between Houston and Mars, for example, could be nearly instantaneous as opposed to taking 12 or 18 minutes or however long it might take?
So the short answer is, while Einstein used to talk about spooky action at a distance, and this is why he didn't like certain aspects of quantum mechanics, right? The short answer is, as far as we know, it is not possible to use quantum entanglement to send messages faster than light. We can have a longer discussion later, but you can have correlations that seem to develop very, very quickly, but you can't, no matter how clever you are, no matter how prosaic or complicated an apparatus you try and come up with, you cannot, it would appear you cannot use that to send messages.
Okay, then the second question is, there have been a number of universities which have taken a stand against the persecution of people of Chinese descent and Chinese heritage who are either in school or teaching or operating out of university academies and institutes. Has Rice done anything to stand up for people of Asian, especially Chinese descent?
Yeah, maybe I should answer that as a dean. Yes, I mean, we have a very clear policy at Rice to protect everybody against any kind of investigation or persecution based on any, whether it's Asian descent or any other descent.
I don't mean domestically, but I mean to act upon the national government, because the FBI and other institutions.
Yeah, my understanding is that, at least among universities, it's become pretty uniform that there's been concern, because we thrive on our international relationships. I mean, the space studies are the epitome of great international interactions.
Right. Well, there's a whole...
And so the reaction has been to really work at making sure we safeguard people. Yeah, so I'm comfortable with. There was a lot of concern initially among people who were here from overseas, but I think it's settled down. And do you have a question?
A woman first.
Okay, please.
Yeah. Hello, my name is Chastity, and I was just wondering.
Just
tilt it down toward your. There you go.
Yeah.
There.
Can everybody hear me?
Yes.
Okay, great. So I know back in the day when we went to the moon, I wasn't alive, but everyone says there was a great black and white live stream. So I'm wondering what kind of cool cameras and technology we'll be able to watch this on now, if we're at home when we get to go to the moon again.
I'm assuming that, it's a shame the NASA administrator's outside having wine. I'm assuming everything is going to be done in full 4K or 8K HD.
Latest.
The moon is close. Bandwidth shouldn't be that bad. HDTV.
And then my second question was, so I know last time we only sent one person to the moon. If at any point in history do you think it will be possible to send a group of people? Because in my mind, it's like even if we send them with the latest neural chip technology, you really don't know what else is up there until you get there. So what if there are some other people that come up, hold them at gunpoint, or like, hey, we messed with your live feed, no one sees anything? You never really know.
I think there's plenty of plans to send larger numbers of people.
It's a good deal. You can do that. Cool.
So last question over here.
So recently there's a lot of talk about how do we build this type of human capital, human resource for the next generation. Like there's a lot of models on whether people should build a very, very broad background or people should specialize or people should build this kind of T-shaped type of educational background. So if we're looking to build the next generation of researcher, what type of educational background, whether it's broad or deep or actually deep in several areas or something of that sort, should the individual aim for?
Yes. No, I can tell you a little bit just to help. I think you have to have a broad education. There's no way these days that you shouldn't have a broad education. At the same time, you have to be good, very good in one thing. But you should know enough of the other fields so you know how to communicate with people. Because the problems you have now, you have to do it. And more important these days than we didn't do in the past, we have to teach people to learn how to learn new things very fast. You're not training people with one training and then you have that train all your life. You have to learn people with the ability to adapt and learn new things. So the combination of these three things, I think, is what's necessary on the new education.
Yeah, I would add to that just that one of the things that we have learned, I think, primarily from business, is that when you get out of a university, you must know how to work in a team. And so we're bringing team-type experiences down as farther and farther. So undergraduate research teams to do research and things like that, because we can't know everything, and it's much more effective to have a group of people who each have expertise but can speak to each other, which is what Jose was saying. So thank you very much to the panel and the audience.
Thank you, Peter. Thank you all. My pattern recognition software is telling me that there's food being consumed and alcohol being drunk outside. So thank you all. You know my usual tagline from the Blues Brothers, you don't have to go home, but you can't stay here. Thank you for joining us tonight, and we'll see you out in the reception area. Thank you all.
That's why you do